All right. Welcome, everybody, to Lecture 9 of PSTAT100. Thank you again for putting up with my travel and these remote lectures. I hope it isn't too disruptive for anybody's studies. Um, but if anybody would like, I mentioned in lecture that anybody who feels like they would like to go through uh, these topics as we start our discussion on linear regression in person. I'll be holding some in-person sessions once I'm back in Santa Barbara, where I'm happy to go through things a bit more carefully if it's new. Last week we looked at probability theory and statistics. Hopefully, it was more of a refresher for most people, um, but it should hopefully have given us the foundational understanding that we need to now study linear regression as we sort of progress in the course and move on to looking at modeling in general, starting with statistical modeling and simple linear regression is one of the simplest statistical models we can start with. So to start with the overview, the aims of this lecture are to start by understanding what we mean by regression and thinking of it as this estimating the conditional expectation, where y is the variable we're trying to predict and x are these variables that are providing information on how to predict with y. So it's our best guess of what y should be given our information about x. We'll outline the simple linear regression model and the Gauss-Markov assumptions that underpin it. So as I've discussed in previous lectures, statistical models have this probabilistic mathematical assumption underneath them. And what makes them statistical is that we then estimate the parameters of those models using data. We'll talk about that estimation procedure, which is called ordinary least squares, and it's this intimate relationship with maximum likelihood estimation and the equivalence of the estimators from these two methodologies. Talking about the properties of ordinary least squares, so talking about how the parameters that we estimate using this method are unbiased, and talking about their sampling variance as well as the fact that they're blue estimators, which stands for best linear unbiased estimator. We'll talk about what that means a bit later on. There are lots of different types of optimal estimators, and so this is one category of estimator. And then we'll talk about inference on these parameters. So once we've fitted our model, we would like to be able to tell anybody who's interested and also inform ourselves about how good those parameters are and understanding the confidence intervals. So how sure are we of our predictions on the coefficient we've estimated for the regressions? And then finally, having a discussion about the goodness of fit of the model, talking about these different parameters. Sorry, I shouldn't say parameters. These different measures that we can use to evaluate how well our model fits the data, and how we compute them in Python. So in terms of the Python versus theoretical component, this is very much the theoretical outline with some Python visualizations, and then in Thursday's lecture we'll cover a specific Python application of simple linear regression. The reason why this doesn't focus too much on the Python code is that the code itself is very simple due to how simple the models are. And so there's not a lot of new syntax to cover, but a lot of the outputs of the models require us to have this kind of background understanding about what's happening. So that's why this library doesn't require any new modules being added. Next lecture we're talking about like stats models, where we'll use functions that perform ordinary least squares automatically. But for the sake of this lecture, all of our computations will be manual, and we'll define the functions ourselves, which are automated by these packages. So I wanted to start by introducing linear regression, trying to understand what regression means. I think that's the most important thing. So we've discussed already in lecture 7, when we covered about probability, what conditional expectation is, and this idea about it's the what our understanding of what we expect the response y to be given some predictor inputs. So x is the information that we have, and we're trying to use that information to predict y. This is, generally speaking, the regression function that we're trying to estimate. So there is, the idea is that this conditional expectation is unknown, and we are trying to describe it mathematically. It's this theoretical optimal prediction of y given x, and that is what the task of regression is. So regression is the task of estimating this conditional expectation function. Just for this, I potentially should have used a different notation because mu can get mixed up with the mean. In this case, mu doesn't mean the mean, it's just a general function. But the idea is that we have some function of these inputs x that produce this best estimate of what y is given some observations of data. And we fit this model using those observations of the data. So this is where I realized I need to shrink my head down a little bit. So I'll move myself more into the corner. So the reason why we impose linearity on mu, because essentially what we're doing with linear regression is we assume that mu x takes this linear form. The reason is that the reason I wrote mu x originally is because this is just some general function. It can take any shape and any form. But in order to be able to estimate it, we essentially need to parameterize it. So we need to assume some structure, and this is always the standard approach in statistics. This is why in statistical modeling, this is why they tend to have much better structure, but they don't focus so much on predictability like machine learning models. In order for us to be able to estimate the model statistically, we need to impose some kind of assumptions, kind of constrain the model to something simple and well structured that we can make computations with. Linear regression, as you'd expect, basically assumes that this conditional expectation takes the form of a linear equation in X. So a linear equation is just it's this kind of weighted sum of parameters, and it's important to emphasize that this is a modeling choice. It's chosen because it's very tractable with small n. It's very interpretable. Like we can understand what a linear model should look like. But as you can imagine, it's very restrictive. It's restrictive to cases where there is this underlying linear relationship between variables, and that might not always be the case. And that's something we'll discuss at length over the next couple of courses in terms of when do we apply linear regression and what kind of exploration can we do to know when we are able to apply linear regression, and then testing whether or not our initial assumption of being able to use linear regression was valid using residuals. So to give a quick foreshadowing of what we're doing in this lecture. So in terms of the terminology, simple linear regression just means we have one predictor. So we have a collection of variables in a data set, and we label the variable of interest that we would like to model y, and we call it the response variable. And then we have, in simple linear regression, we choose a single other variable, and that variable is going to be our predictor. And we're assuming that the predictor variable contains some information with which we can predict the outcome of y. So multiple linear regression just assumes that we have multiple predictors. It generalizes to, p predictors is the standard syntax. This is something we'll discuss next week when we consider more complicated scenarios. But and things like multiple regression, and also things like polynomial regression and additional kind of tweaks we do to this underlying assumption, which makes it more complex but potentially more flexible to different situations we may encounter in the data. So linear just refers to the linearity of the parameters. So this is just a quick note to specify that we could potentially include things like squared variables, and that doesn't matter. That doesn't become polynomial regression if all of the parameters themselves are if the model itself is linear in the parameters beta, it's called a linear model. But you can see this is the second bullet point is an example of a nonlinear model. We have this exponential function which introduces nonlinearity, and this is just a very quick example of a model structure that we could not use linear regression to estimate for. And obviously, much of machine learning you can view as this more flexible non-linear regression, which is why we can't understand its structure. We don't impose this linear restriction initially in the model, which gives the model flexibility, but then we sacrifice the ability to interpret it in an easy to digest way. So regression is technically a type of supervised learning framework. Supervised learning, like I mentioned before in class, is just this idea that you have your response, you have some kind of targets that you can use to fit the data, some true values, which can give you errors, and you can use those errors to kind of tweak and hone your model. And in this case, linear regression is when we have this continuous variable, this continuous response y. So some examples would be like house price, temperature, body mass, anything that you can model using, anything that's modeled with continuous data. So the simple linear regression model. So the key formulation is that we assume a data generating process can be written in this linear form, where yi is the response and xi is the observed predictor value. So we use the lowercase notation here, the lowercase x, to denote data. So if this was a capital X, that capital X would be the random variable used to generate that data, and you could be considering this this would be an expression of combination of some function of a random variable X. But in this case, we have our response, which is random. We have our observations, lowercase x, which are fixed. They're not random because we have these. We have n observations, and then we have epsilon, which in this case is the error. So this represents the deviation of our response from the line. And this captures all the unexplained variability. So this is where we capture the randomness. We're assuming that there is this deterministic linear relationship between y and x, plus this noise component, which is captured in the error. In simple linear regression, we have two parameters. We have the intercept and the slope. The intercept is just the expected value of y when the observation is 0. This is typically not something we're hugely interested in, but sometimes it can be important. Beta 1 is more the variable we're interested in. This is this expected change in y per 1 unit increase in x. So as x changes, how does y change? And as I just mentioned, this you can think about the beta 0 plus beta 1 xi as the systemic part. So this is systematic, sorry. This is the fixed deterministic part, and the random part is all captured within the noise. Okay, so the Gauss-Markov assumptions are essentially the underlying conditions needed for linear regression. These underlying assumptions that dictate the structure of the model. So number one is linearity, and that's this idea that the expected value of the noise is 0 for all I. So after you have fed in your observation x and transformed it to this by this linear relationship to y minus the noise, all of the noise is centered around this line. The next is independence, so that each of the noise iterations don't have any dependence on what the previous noise was. It just means that if you're generating, you think about this data generating process as generating these multiple observations of the data that we're considering. Whatever the previous noise was has absolutely no influence in what this next noise is, and that's just think these as a sequence of independent, identically distributed random variables. Homoscedasticity is this idea that the variance is constant across all of the observations. So there's no fluctuations of the variance or no dependence on the variance of the noise based on the observation, as well as the observations change. And then number 4 is normality, which is that these errors themselves follow a normal distribution with this constant variance from the homoscedasticity as the variance of the random variable. We'll note a bit later on that this is required for exact inference with small n. It's asymptotically justified in general for by the central limit theorem for large n. And so it becomes, it's the least important of these 3 initial observations because it tends to always be satisfied for large n anyway, when we use a central limit theorem. Combining these together, we get this expression that that y's can be interpreted as this independent, identically distributed sequence of, maybe I shouldn't say identically distributed because they're all dependent on xi. But anyway, I'll be more careful with my notation, but this independent sequence of random variables with this mean that depends on the data x, but then this constant variance. Okay, and you can work that out relatively quickly by just using the fact that from this expression, we see that if I use my pen, or my mouse, I should say, nothing here is random. So this is just, these are just some kind of function of fixed values. This is assumed to be a normal random variable. So this is just some shift applied to the mean of a normal random variable. And then since this doesn't contribute anything to the variance, the variance of this follows through to the variance of y. So we end up with this shifted, sorry, I shouldn't have gone back, but we end up with this, instead of being centered at 0, it's the mean is shifted over by that expression, and then the variance stays the same as the noise. So visualizing the model. This is, I skimmed over this code quickly because this is essentially just applying a linear function to the noise. So if I kind of highlight what's happening in the code here, you can see that I specify our parameters on this line, and just specifying some intercept point beta 0, some slope beta 1, and I'm generating values uniformly on the interval 0 to 10. I apply this transformation where x gets fed into this linear expression. So this isn't doing any generation, any randomness. I just apply this noise term after the fact, which is just a standard normal. Sorry, I shouldn't say standard normal, just a normal random variable centered at 0 with standard deviation given by sigma, which we defined up here. And so this is essentially the perturbation from the lines. So if we ignored everything after the plus, we would just get a perfectly straight line. And then this is generating the sort of noisiness of the data around that line, which is what you see here. So the noise terms are what's pushing these terms off the line that we've fitted them from. So this is why in this case, this best fit line is the true line. The true line is, this data was generated using this true line. So we know this is the true, I shouldn't say best fit because it's not, it's the true line that was used to generate the data. So just to add some visualization for the error terms, you don't need to understand this code. It's more just to show the how to think of the errors. And this is all this is doing. It's just doing a computation to determine the error and its location. But you can think of the error as this vertical distance of the point away from the line. Okay, so obviously this point, the generated noise that produced this point was much larger on average than the rest, or not much larger, but this was a significantly larger one, and these were significantly smaller. Okay, I need to watch the time because I don't have a clock or students to remind me. My stopwatch seems to have stopped. Okay, 16 minutes. Okay, so we now have the mathematical underpinnings of the model. Let's kind of big picture time. We're thinking about, we have some observations with which we want to use to describe a response. We want to be able to model a response using some observations. We've defined this linear relationship, going back to this, I shouldn't keep going like this because it's very inefficient. We've defined this as our modeling structure, and we've constructed 3 parameters that we need to fit. We would like to compute beta 0, beta 1, and sigma squared, and we would like to do so such that the resulting line that we would produce is as close as possible to the true line in this case, that you're assuming is there. In our case, we know it's there because that's how we simulated our data, but in the real world, you will have some data that you assume has this linear relationship, and you use, you would try and compute what these parameters are to make that line as good a guess as possible to describe the underlying relationship. So that raises the question: is how do we do that? How do we predict these? How do we estimate these parameters? And the answer is to use ordinary least squares estimation. So what is that? What is ordinary least squares estimation? This idea of choosing the best fit line. So we have some data and we would like to try and fit a best fit line. And so obviously, we take beta 0 and beta 1 as unknown. We're estimating them from the data. And the idea that we can apply is that we can propose some candidate of these parameters, beta 0 and beta 1. And we can, for that candidate line, we can compute the estimated output, and then use that estimated output to compute the error. So you can see in this line describing the error is given by whatever the true observation is from our data minus y hat, which is what our best guess is based on the parameters we've selected. So these errors correspond to this B0 and B1 that we've initially picked. And the idea is that in ordinary least squares, we would like to find, sorry, I should say in ordinary least squares, we use something called the residual sum of squares. So the idea is we take this error and we square each one in order to remove the negativity, but also to make sure that it's differentiable. I'll talk about that in a second. And we sum them all up. So the idea of the residual sum of squares is that we pick some option for the parameters beta 0 and beta 1. We compute the errors. So what point of y does it predict, and what's the true point of y? What's the difference? We square all of those errors and then we add them all up. And that is our measure of how good this parameter choice was, because this is going to be larger. If these errors are larger, this is going to be larger. And so the idea is that we want to minimize this residual sum of squares as much as we possibly can. And we could do that by obviously iterating and just doing sort of a brute force search. You could choose multiple different B0s along a range of values and then multiple values of B1 and just brute force compute them and find the minimum. But thankfully, in this case, because we've chosen the residual sum of squares, because there are many different options we could choose for this loss function, this measure of fit. You know, we didn't necessarily need to just square and then sum them. We could have squared them and then square rooted them. We could have had like the absolute values instead. But the benefit of it being of squaring is that it makes the criterion differentiable, as well as also penalizing large deviations heavily. So the squaring, this kind of exponential growth, heavily penalizes these large errors, more so the bigger they get. And so it has this combined effect of it makes it making it both better for penalizing large deviations, but also it makes it solvable analytically. So as I mentioned in previous classes, and I keep saying that, I apologize, but one of the great benefits of simple linear regression and linear regression in general is that we can have these closed form solutions for our estimates. And we can do that using the methods we've learned in calculus, whereby we have, if we have a differentiable function, if we compute the derivative with respect to what we're minimizing over, we can then find the maximum and min values. So that is our plan going forward, is that now we have this residual sum of squares. If we differentiate with respect to B0 and B1, we can then solve those by setting those equal to 0 and solving those equations to hopefully receive some closed form solutions for the parameters. And that is the method of ordinary least squares estimation. So we take the partial derivatives with respect to B0 and B1 and set them equal to 0. So you can see here the only difference between on the value on the left is this drss by dB0, and the one on the right is drss by dB1. The only difference is that the one on the right has this xi following through, because we can see that when we differentiate with B1, we're going to have, and using the chain, both of these are using the chain rule. I'll do a bit of writing on my iPad to break down some of the computations on this page because it's the most important part. But the idea is that we can solve these equations, and I'll go through how to do that in a second, to get these closed form solutions. So we get that we're essentially found, I should have changed in here, but once we set it to 0, this becomes beta hat 0 and beta hat 1, and beta hat 0 and beta hat 1. So this is what we've solved for. And we can write it in this term. So this is relatively easy to derive from this expression. And then we through a bit of algebraic manipulation, we end up with this expression for beta 1. So if I can just switch, I'll just switch quickly to my iPad and we'll go through this computation. If I can do it quickly, I practiced this as I was going, but we'll try. Okay. So the idea is that we have, let me just quickly write out the, so I'll write it as something like a loss function. So I'll do something like RLRSS beta 0, beta 1 is equal to this sum of yi minus b0 minus b1 xi squared. So if we take the derivative with respect to b naught, we're going to get everything in the sum differentiates on its own. So we can essentially just forget about the sum and differentiate everything inside. So we're going to get, from the chain rule, 2 times yi minus b naught minus b1 xi. Power reduces to 1. And this is times by the derivative of b naught with respect negative b naught with respect to b naught. So that becomes times negative 1. So this becomes minus 2 I equals 1n yi minus b naught minus b1 xi. And then similarly, hopefully it's clear why then if we do by b1, everything on the first step is going to be the same because it's the same function. So we're going to get 2 yi minus b naught minus b1 xi. But this time it's going to be times by the derivative of this guy. So this is going to times by minus b xi because it's derivative with respect to b1. So this now becomes minus 2 I equals 1n xi yi minus b naught minus b1 xi. Okay, so that's how we get these two expressions that we saw on the second slide. So I'll highlight them. So to find beta hat naught and beta hat 1, we set to 0. So this becomes minus 2 yi minus beta hat naught minus beta hat 1 xi equals 0, and minus 2 n xi yi minus beta hat naught minus beta hat 1 xi equals 0. Okay, I'll just call this 1 and this 2 for the sake of notation, making it clear. So considering 1, we have, let's first kind of go through converting all of the sums with respect to the variables in I. So I think I have a pointer. Do I have a pointer? I have like a little hand? No, it's just like a thing. Like this guy. So let's convert this sum of all these different variables into n times the mean. So this is going to become minus 2 times by n y bar minus beta hat naught minus beta hat 1 nx bar. Oh, sorry, this is also n. So n beta hat naught, because it's a sum of n of them, minus n beta hat 1 xi. And that's hopefully clear why we can cancel n throughout, because n can't be 0 and minus 2 can't be 0. So this just becomes y bar minus beta hat naught minus beta hat 1 xi x bar. Sorry. Equals 0. And this is why we can write our first expression, which I'm going to make sure I get in the right form. We have this beta hat naught is equal to y bar minus beta hat 1 x bar. So this is our first expression. So now if we can get a closed form expression for beta hat 1, we can substitute that in, as long as they don't depend on each other. If they depend on each other, we just have to cancel them out from each other. But let's consider 2. So we have that. We'll do the exact same trick. So minus 2 well, I can cancel the minus 2 straight away, but I'll write down the sum. So I equals 1n xi yi minus beta hat naught times by the sum. I'm skipping steps just in case. I'll go I equals 1 n xi yi minus beta hat naught xi minus beta hat 1 xi squared equals 0. So then this is just equal to minus plugging in our value. We have y bar minus beta hat 1 x bar times xi minus beta hat 1 xi squared equals 0. And this is all included in the sum. So I'll just be a bit careful with these brackets so that we all know. So this then is equal to 1 and xi, yi, and then minus y bar sum I equals 1 n xi plus beta hat 1 x bar sum I equals 1 n xi minus beta hat 1 sum I equals 1 n xi squared equals 0. Moving these terms, I'll just do it in pencil, moving these terms across to the other side, and then factorizing out beta 1, we end up with beta 1 hat is equal to everything on the left-hand side, so sum I equals 1 n xi yi minus y bar I equals 1 n xi, and this is divided by, this is going to be positive, so this is going to be I equals 1 n xi squared minus x bar I equals 1 n xi. All right. So this is not quite what we had. So in terms of from the slides, we have that beta 1 hat is equal to sxy over sxx, which is equal to sum of 1 I equals 1 n xi minus x bar yi minus y bar, and then over sxx, which is equal to equals 1 n xi minus x bar all squared. Okay, so we can show the equivalence to these expressions. I like doing it this way around because it helps, it saves us just introducing things to get to this result, which is what we need to do. But we can see that if we take sxy, we have this sum. If we expand out the sum, we have xi, yi minus x bar sum I equals 1 n yi minus y bar sum I equals 1 n xi minus, or sorry, plus n x bar y bar. All right. So this is matching at the start. So we need to show all of this equals this second term up here. Well, we need to basically show that this term and this term cancel. But we can see that cancel straight away because this is going to be written as minus x bar times by n y bar. And then this is just cancel plus n x bar y bar. So these cancel. Right, so you can cancel these guys and you end up with what we got. So we can write up here, this is equal to s xy. And then for the second, the base of this expression, or the denominator, I should say, we have a little bit more computation to make. Let me just check my notes because things got messy last time I did this. And maybe it's not even something that's worth going through, but we can try starting with sxx. We have this multiplying it out, we have xi squared minus 2x bar I equals 1 n xi plus n x bar squared. Okay, and we want to show that's the same. So we essentially want to consider, we have the start is already the same. So this sum xi squared is the same as, if I get my pointer out, this is already here, so we just need to show that this is equal to this. So we can see here that this is going to be equal to 2 x bar n x bar plus n x bar squared. So then these two together equal this minus x bar n, minus n x bar squared, which is equal to minus x bar sum I equals 1 n xi as we needed. So then this is equal to sxx. So a little bit of messy computation, but you can see that just by performing this computation, you end up with the result we quoted in class. So I'll do a tick to say that we got to where we needed to go, and I'll do this highlighted so that when I add it to add it on the Canvas page, people can see it. But the point now is these obviously depend only on the data. So these guys both depend on the data, and so we can compute the slope directly from the data, and then from that we can immediately compute the intercept. All right, so that's the key kind of derivation of these results in linear regression. So let me just switch back to my lecture slides now. Hello again. So, key insights. The OLS line always passes through the sample means. Because of this derivation, you can see why it's always going to pass through the sample means from here. And this estimate for the best estimate for the slope is always proportional to the sample covariance of x and y. This is what this is describing here. So this is the variance of this covariance of x and y is appearing in here. So there's always this dependence built into the slope of how the size of the covariance between these two variables. A quick aside, we can just do some quick maximum likelihood estimations. So far we've considered ordinary least squared estimation, and in earlier lectures I discussed with you how maximum likelihood estimation is also a way we can compute these. And to kind of show the equivalence between these two methods, they aren't the same method, but their estimates produced for linear regression are the same, as long as we have this fourth Gaussian condition of normality, this Gaussian Markov condition, sorry. So as I mentioned in a previous slide, when we have these conditions, we have that the data generating process can be considered realizations of these normal random variables, independent realizations, but with mean dependent on x. And so we can compute the likelihood function. And I only briefly discussed this, so please do come and see me if this is confusing. But essentially, the likelihood function is computed as this, because they're independent, we can write this joint distribution as a product of each of the marginals for each of the variables, of each of the observations I. And from that, we get this product of essentially just a Gaussian density function. So 1 over 2 pi sigma squared, or 1 over root 2 pi sigma squared exponential of minus yi minus the mean. And in this case, the mean is beta 0 plus beta 1 x1. And so this is minus the mean from here divided by sigma squared. So the sigma squared is coming from this part. And because we take a product, this has no dependence on I, so this just becomes to the n minus a half because it's 1 over the square root. And then once the product goes in the exponential, because the exponential is e to the power of something, this becomes a sum of powers. And so we take out everything that doesn't depend on I, and we end up with this sum in here. Hopefully people can already see where things are coming from. So you can see by taking the log likelihood of this function, we end up with this expression in terms of the variance. And then in here, we have this negative 1/2, and then the sum of yi minus beta 0 minus beta 1 xi all squared. And this is the same as our RSS, right? This is the same as our residual sum of squares. So you can imagine that when we then continue our method using maximum likelihood estimation, our process is to differentiate with respect to each one of these variables. And if we differentiate with respect to beta 0, this goes away and this goes away, and we end up with, we're essentially taking the derivative of RSS with respect to B naught, and we end up with the same expressions on the previous page, which we can then use to compute the best estimators. So the takeaway, you complete, if you are interested, please do go through the mathematics yourself on this problem. It can be quite enlightening to see how lots of these different statistical methods can arrive at the same estimators, because they're all designed to get to the best estimator they can. And so if the best estimator is very tractable and easy to compute, as is the case in with this linear assumption, they often arrive at the same value. So the kind of takeaway is that you can have multiple ways of estimating parameters, but in this case, the ordinary least squared is the same as the maximum likelihood estimation. Okay. So here is just some Python code performing these computations for some data. So we're taking the data that I used to generate the first plot. So this kind of artificially simulated, linearly related response and predictor. And we're just computing all of these values that we've just specified mathematically. So we compute the mean, we compute the mean of both x and y, we compute SXX and SXY, and this is just using the expressions we just derived. From them, you can then compute what beta 1 hat is. So beta 1, this is our estimate for beta 1, and this is our estimate for beta 0 using, again, our data. And this is just some code printing our estimates alongside the true values, as well as our line corresponding to those values. So remember that we've estimated the intercept and the gradient of a line. And so we can use that and compare this estimate of what we think the best fit line is against the true line in this case, which is what we use to generate the data. And you can see here, it's quite good, as you'd expect. So the true line and the ordinary least squares are very, very close together. And you can see the discrepancy between the true and the estimated here. The biggest discrepancy is with this beta naught, but like I said, most of the time, we're not as interested in the beta naught because this discrepancy depends very much on the scale of the data. And you can see, although it looks like a large discrepancy here because it's essentially double or essentially half, sorry, what our true value is, the data is ranging from 0 to nearly 20. And so this is a relatively close approximation of each other, but the slope is nice and close, and the two lines nearly lie on top of each other. Okay, so this is all that's happening with the linear regression model. I think that's, and sorry to go on a tangent, but I always think that's very interesting. I think it's such an interesting, deceptively simple, if you get past the algebra, way of computing these parameters and being able to always fit this best fitting straight line to data based on the residuals that you've computed. So just to be, I've been using the terminology residuals, but I realized that I maybe put this definition too late in the lecture. But the fitted value is this, what we use once we have computed our optimal parameters, we can then compute our optimal predictions. So once we've fitted the OLS parameters, we can then use them to generate our fitted values based using each of our observations xi. And then we define the residual to be the difference between the true value and this optimal prediction that we've obtained. I won't go over this too much just for time, because I'm already going over time, as I always do in class as well. It doesn't help that my phone keeps turning off its timer. So I've got about 30 minutes left. I'm about halfway through, so yeah, we'll see. But anyway, the residuals sum to 0. The residuals are uncorrelated with x, and the residuals are uncorrelated with the fitted values. So these expressions you can reverse engineer by taking EI, plugging in YI minus Y bar, and then plugging in B naught hat plus B1 hat XI and computing all of these sums. And you end up with these results. But essentially, this is just a feature of this type of parameter estimation. The reason why all of these go to 0 is we're by design assuming that the noise, which is essentially what this EI is a generated process of under our model, this is what we predict the noise values to take. And by assumption of our mathematical structure, when we fit this model, these properties hold. Okay, which is what it means when I say they follow from the normal equations. So you can reverse engineer these properties by reverse engineering. You can reverse engineer them by reverse engineering by plugging back in EI, then YI hat, and then doing the computations with the resulting expressions, the algebra, and they'll follow through. So just to show some empirical evidence of this being true, we compute these for our simulated case. You can see here, I very much used Claude to help me write these code outputs because I couldn't be bothered keep typing in all of these different symbols, just so they'd appear nicely in the code format. I don't think it was worth it, but I quite like the formatting change. We are taking our estimates for the parameters of the simple linear regression. We are computing all of the different estimates for the fitted values. This is using vector notation. So here X is this vector of values we defined earlier. And then we can compute this vector of the residuals as just the difference between the true Y and this estimate for Y. And the residual sum times X, and the residuals times by Y hat, all summed. So, and they're all tiny. We can see from the output, they're very, very nearly zero. I mean, as close as you can get in Python. I think maybe you can get like 20s and 30s actually for exponential, but as near as makes no difference, zero. Okay, so just to visualize them on our plot, again, you don't need to worry about this too much. This isn't really super applicable, but you can use this code if you ever want to make similar visualizations for yourself. The residuals are the difference between the fitted line from the OLS. So this isn't, I apologize. I should have used the same formatting. I think I used a dashed line for the OSS line and then a red line for the true line. This line is our fitted line. So this is these aren't the true errors because we don't know what the true line is. The residuals are the distance between our best fitted line under OLS and the true observations vertically, the vertical distance. I'm going to sip of tea because I'm losing my voice. It's cold because I've been talking for 40 minutes. How disappointing. Okay, so I've spoken about how we estimate these parameters, these estimators, I should say. Let's go through some of the properties of these estimators that make them so good. And we've talked about this before when we talked about statistics and inference. We talked about bias of estimators, which is this, does our parameter, which is it's a statistic and it's a random variable, and with some distribution. And the point of something being biased is that in expectation, this random variable gives the true value. The expectation of this random variable describing the estimator lies on the true value. So we can confirm, in fact, that the OLS recovers the true parameters on average. So it means it's unbiased. The algebra for this is, again, a little bit messy, but relatively straightforward. I've tried to kind of break down the intermediate steps for kind of showing this more easily. The idea is that you can write, I did this just for beta hat 1. You can see the same result online for beta hat 0, but to show how this is computed for beta hat 1, we can write this as this sum of Ci times Yi, and where Ci is this Xi minus X bar over Sxx. So this is just following from the normal equations that we defined earlier. We can essentially just break up Sxy into this Ci times Yi, and then have the sum outside. And then since we can write Yi using the kind of assumed model equation, we can start plugging in these values, and you can see that everything starts to cancel away. So I take this expectation of b hat 1, plugging in b hat 1, I get this expectation of the sum of Ci and Yi. Now Ci has absolutely nothing random in it. This is all to do with X. This is all to do with x itself. So CI is all to do with x. The only thing random, all the x's are observed, is the y's, because that's our response. So that's why the expectation just comes onto the individual y's. And then we can use this expression for y to expand everything out, and we see that again, this doesn't have any randomness, so the expectation passes through it. None of this has randomness, so the expectation passes through it, and we're left with the expectation of this, but the expectation of this is 0. So the expectation disappears, and we end up with this in its place instead of the expectation of yi. We just get this part of yi, which is where this decomposition comes from. We have b0 sum of c1 of nothing, because it was just 1, and then plus b1 sum of xi. This is where I'm, just for time, maybe at the end of lecture, I'll add a quick note on this if I get through the next few slides quickly. But you can do this breakdown yourself. You essentially take this expression for CI, which is this term here, and you can show that you can basically disregard the denominator. You want to show that it is equal to 0, and so you can show that the sum of xi minus x bar is equal to nx bar minus nx bar, and you can hopefully see where that's coming from. And the numerator then goes to 0 until the whole thing goes to 0. Similarly for this one's maybe the more tricky one. We take cxi xi, plugging into this, we have xi times xi minus x bar. That, if you expand that out with the sum, you realize this whole expression becomes sxx over sxx, and this becomes, that means it's equal to 1. And so this goes away, and then you're left with beta 1, and it's unbiased. Like I said, I'll include a note that goes through this, posted with the lecture notes. But the main point is, if you're interested, you can go through the algebra, but we can show that the expectation of these estimates are equal to the parameters, which means it's unbiased. You can also note that the normality wasn't needed. We just used 3 primarily for this, but we didn't assume normality through this, which is, this kind of leads to this conclusion that of what we talked about before, about how we don't really need the normality unless we're considering very large, small numbers of n, and even then we use the t distribution. So, okay, so for the sake of brevity, I was going to kind of derive these expressions, but I'll skip through it. So the sampling variances for these parameters are given on the lecture slides. Variance of beta 1 and beta 0. These, again, we can derive using the standard procedure, but the fact that everything is essentially either not random or has the noise term, and so it's essentially just functions of the variance of the noise term, which is why the sigma squared follows through in both. But we write it in this form because we can interpret what drives precision. So the idea is that we would like this, if we want the sampling distributions of the two parameters to be as narrow as possible, what can we do? And we say, well, if we notice that if we have more spread in x, then this sxx term will increase, and that will, in general, because they're both in the denominator, decrease the variance. So if we have a very spread x, we have the variance, the distribution around our estimates for the parameters gets tighter and tighter. The sampling distribution of our parameters gets tighter and tighter. This is something called leverage. Better leverage is the idea of if the points are further away from the line, they have more leverage and more ability to control that line. Similarly, if we have a larger sample size, we can see this n appearing in the denominator. So that's driving down the variance because we essentially just have more information. It's kind of typically what we see with all expressions in terms of statistics. If we have a larger n, then we decrease the variance. And similarly, if the noise itself decreases, so if the true noise driving the spread of the data decreases, then so do the variance of these two of the sampling distributions of these two parameters. Essentially, because we're using the model, we're assuming the underlying data has this linear relationship plus some Gaussian noise component, and if that noise component has less variance, then there's essentially less noise. The signal is cleaner, and we have a much kind of more linear distribution or kind of closer distribution of the estimates around the true line. Oh shoot, I didn't know this nearly went off the page, but a lot of the time, I've spoken in the MLE section that we have these three parameters, sigma squared, and since sigma squared is unknown, we typically estimate it with the residual variance. So we can use our estimates for beta 0 and beta 1 to then compute the residual, and then by computing the residual sum of squares, that is the residual sum of squares is our approximation for the variance of the noise term. However, we note that we have to divide by this n-2, and this is for a similar reason as to why we have to divide by n-1 with the sampling variance of and we've looked at before for things like parameters of like a proportion of sick cats, I think was my last example in the last slide. And when we estimated the sample variance for parameter p, we had to divide by n-1. Or sorry, when we compute the sample variance of a population, we divide by n-1. And that's because the sample variance relies on one estimated term, this mean that we've already computed statistically using the data, which reduces its degrees of freedom. It costs 1 degree of freedom in that case. In this case, because we've estimating sigma hat using two different estimates, one for beta 0 and one for beta 1, that costs us 2 degrees of freedom, which is why we have to divide by n-2. I'll just check the time. About 20 minutes. Okay. So this is just a very quick aside. We're not going to discuss all the various different ways that estimators can be good, but just for the sake of mentioning it, under the first three Gauss-Markov theorem assumptions, the OLS estimators are called BLUE estimators, which stands for best linear unbiased estimators. So the idea is that we know what they mean to be unbiased. Linear just means that the estimator is a linear function of the responses, which holds because of this kind of invertibility of the linearity of the model that we defined in the first place. And the idea of being the best is that among all the linear unbiased estimators, the OLS has the smallest variance. This doesn't mean it's the best estimator. It's the best linear estimator that's also unbiased. You could potentially have biased estimators that have smaller variance. You could also have nonlinear estimators that have both lower bias and lower variance and are just empirically better. But this is a subclass of estimators called linear estimators, and out of all of the linear estimators that are unbiased, the OLS estimators also have the lowest variance. So this is just a very quick simulation of all these properties. You can, not to spend too much time on this code because, like I said, it's all sort of generated, but you can hopefully see the same sort of pattern. Here in my YSIM, I'm using the true parameter values that I defined initially and generating the noise using the sigma that I defined originally, the sigma true, and then computing all of these terms using the definitions that we've just derived, like for beta 1 and for S6i, beta 1 simulations, theoretical. So we're simulating all of the different beta 1s for this range of different samples that we're taking of xi, and just producing a histogram for them. And this is what we get. So this is just a demonstration of we took many, many different simulated samples from our true line with the noise that we're generating. We fitted a best fit line. We computed what, using OLS, what the parameter beta 1 should be. And we're producing the distribution. And you can see that the mean of the distribution lies very, very close to the true value, which is demonstrating that it is not biased. And it's also got this empirical standard error lying very close to the theoretical standard error. So it's highlighting that these results that we computed here, so sigma squared, and then also the previous results for beta 1, the variance of these two. Sorry, in this case, it's this expression combined with this expression is resulting in a very close. They're very close to each other after, I think, 2,000 simulations, right? Yeah. Okay. So we now have the tools and know-how to, without any functions in Python, we can, using some observed data and a single column of, an observation variables column and a single response column, so a column of y's, I guess, and the other one's x, we can determine using ordinary least squares what the optimal parameters are, and then we can use that to create a best fit line with which we can then compute the residuals, and then from that you can estimate what the sigma squared of the noise is, the sample variance. So we now know how to mathematically compute all of these different parameters. And we've also started to explain the distributions of these various parameters, but this section is specifically interested in more formally using those distributions to make statistical conclusions about the parameters. So some common questions you might ask are whether or not there is significant evidence of a linear relationship. And for that, you would be interested in testing how significant the slope is, etc. And so that's more what we're interested in this last section for the last 15 minutes. So I'll clip out the whole slide, sorry. So we've spoken about this before, but we've used this expression before. We have using this expression as our intuition, we can see that our parameter for beta hat 1 can be written as this linear combination of independent normals. So y has a normal distribution. Ci doesn't have any distribution. And so this is essentially just a sum of normal random variables, of independent normal random variables. And we can use that to show that the sampling distribution of beta hat 1 is itself normal, centered, as we've shown using the bias at beta 1, and then with the variance that we approximated in the previous couple of slides. In this case, we haven't yet replaced, if we knew what the underlying noise was, we could use this normal distribution. But when we don't know, as with kind of normal statistical inference in Gaussian statistical inference that we've seen before, we replace it with the standard deviation, the sample standard deviation. I apologize if my terminology here maybe is a little bit unclear. I'll be careful to be more precise in the lecture notes. I'll see if there's a more kind of rigorous way of defining of using this notation. But this is essentially I use the subscript to show whether it's the sample computation of the standard deviation or the deviation of the sampling distributions. So in this case, this is the essentially the standard error of the sampling distribution of beta 1 hat, and this is the standard error of the observations itself. So the idea is that into this expression, we wrote this on the previous slide. We compute the standard error of the estimate for beta 1 as sx be s beta 1 hat all squared equals sx squared over sxx. Yeah, I definitely should use a different terminology there because saying that is difficult, but hopefully visually it's clearer. And obviously then the square root of the variance is just given by sx over the root of sxx. And then this is what we plug into the down here in our expression, because this is, if we remember with the student's t-distribution, the student t-distribution is always centered at naught, so we always have to standardize. So we're standardizing this beta hat by subtracting beta 1 and then dividing by this estimate, which is given by nearly by this, but replacing sigma by sx. And because of that, we're using all of these different parameters that we've estimated from the data, these estimators that we've estimated from the data, the resulting student t distribution has n minus 2 degrees of freedom, right? Because we've used beta 0 and beta 1 as our two parameters that we've already estimated. Okay, so this is a constant expression. It's always going to be n minus 2 for simple linear regression because we only ever compute beta 1 and beta 0. But you can imagine as soon as we have, say, 5 different, in multivariate linear regression, we have 5 different beta 0 up to beta 5. We're going to have this degrees of freedom is more important to think about. We're going to have n minus p degrees of freedom in that case. I'll discuss more about that later. So, as I mentioned, all of these have analogous results for beta hat, but because we're typically more interested in the slope, I've kind of saved space by not including them, but they'll be in the lecture notes. This is what I mentioned before. This is one of the most common tests that you care about. You care about testing whether the predictor has a linear effect, and so that's testing whether or not the beta 1 is 0 or not. So you're under the null hypothesis, you assume it is 0, and under the alternate, you assume it isn't. So this is going to be a two-tailed test. You can then use this test statistic and a p-value. So you've just shown the test statistic t from the previous slide is beta hat 1 minus the true value, beta 1. But in this case, under the null, you're assuming it's 0, which is why it goes away. This, has a student t distribution with n minus 2 degrees of freedom. And then you can compute the p-value in this two-tailed test using this computation, which is hopefully something everyone's familiar with. It's essentially computing the probability that your observation, what you've observed, so plugging in the actual data points for t, is at least, what's the likelihood or what's the probability of seeing an observation at least as extreme as your observation. So you're basically saying, okay, let's sum up all of the probability of seeing any other kind of beta 1 from a different sample and get them, what's the probability of seeing one at least or more extreme than the one I've seen, and combine all that probability into one object and then see whether or not it's significant on a scale that you've set in advance. So typically you'd say the significance level is like 5% or 1%. And so if the probability of getting an extreme value as crazy as yours is 0.01, then it's going to be highly significant. So this is just an example of computing all of this again. This is the new thing that we're using is in here, the student t distribution. I'll have a talk about this sort of using distribution functions in Python in the lab on linear regression. I'll have a section that kind of goes through using normal distribution CDFs and t distribution CDFs and things like that. But this is all the same. This is all just computations using the values we've got. And then this is computing this test statistic t, beta hat 1 over the standard error, which we've already computed up here. And then this is computing the p-value. So this is essentially showing you what's under the hood of all of these linear regression functions, which then produce these table summaries. This is what they're doing. So these are our values. You can see here our p-value is extremely small. So very, very strong evidence that we should reject H0 and conclude that this is not 0, which is what we'd expect from what we've seen already, because we know this data has a strong linear relationship. Let me just quickly check the time again, because I think I'm coming right up to the end of it. I've got about 5 minutes left. Similarly, this is exactly the same procedure. We just use the fact that we know that we have this t distribution scaled by the variance, and this has been centered by 0 because we're assuming it's 0. And so we can construct the confidence intervals in the same way as we would for in normal statistical inference. Typically, any kind of linear output will produce these as well, but just I'll quickly skip to the code that produces it. So you can go through this in more detail, and please come and speak to me in my office hours if you're unsure about how confidence intervals work. You're essentially just doing a slightly different, the same check as p-values, but in a slightly different way. With p-values, you take what your observation is, you determine what it means for an observation to be more extreme than yours, and you compute the probability of that region. In confidence intervals, you start with your significance level, you find out what the values would be in order for the more extreme values to take up 5% of the probability, and then the not so extreme values to take up like 95% of the probability, and then you determine whether or not your value lies inside or outside that bound. So I'll if anyone has any questions about that, please come and discuss it with me, and we can do some examples of confidence intervals and p-values and intuitively understand what they're doing. This is just computing them empirically, again, just using this t-crit as our computing our critical value, again, just using the t-distribution function, which we imported earlier. The last thing I want to talk about, I may go over slightly on this lecture, but I'll try and go under in the next lecture. Plus it's remote, so you can always turn me on, twice speed or something. So decomposing variation. So this is a very important topic that we'll cover a lot more whilst we look through linear regression. We can produce something called the ANOVA identity, which is you can write the total sum of squares as this combination of the contribution of the regression and the contribution of the residual. So we have these three different terms combining together. So the point is that SST measures the total variability in Y. So this is obviously not scaled, but the variance, the sample variance of yi minus the mean. This is the variance of our estimated yi minus the mean, and then this is the sum of the errors, the variance contained in the residuals and the errors. So you can I think I do a plot on a later slide which shows how these guys combine, but you can think about it as the sums of the different lengths from the different lines. So I'll show you in a second. This can be really helpful for us. The reason it's on here is because naturally the linear regression outputs show all of these things, and it allows you to determine where your model is assigning this variance. So you can see what the total variability in Y is going to be, and you can see how much of this variability is explained by the model, by the SSR, and then how much is contained in the error by the SSE. And it gives you this intuition about where the variability is being explained, or where it's being kind of captured by the model. From this, we can derive the R-squared statistic. So the R-squared statistic can be thought of this proportion of variance in Y explained by the linear model. This is just computed as the SSR, so from the residuals over the total. And then that's equal to, because of the sum on the other page, 1 minus the sum squared of the errors over T, sorry. This is not the residuals, my mistake. This is from the regression. This is from the errors. I apologize. I get these mixed up quite a lot. I don't like the SSE, SSR notation personally, but so this is getting a lot of detail. For the time being, it's sufficient to sort of understand how to read them. And if you work more with linear regression, you can try to understand these properties more, particularly if, say, for your final project, you're discussing linear regression. But the main point is that R-squared will always lie between 0 and 1. If R-squared is 0, the model explains nothing. So the idea is that you could just as easily predict a flat line, and it would have fit just as well. If R-squared is 1, all the points lie directly on the line, and it's a perfect fit with all the noise accounted for. For simple linear regression, this R-squared is equal to the square of the correlation coefficient. So if you were to use, I believe it's the core, like the core correlation function that we've looked at in our exploratory data analysis, we get the correlation between different variables. We get this matrix of correlations. That's the same. It comes out in simple linear regression only, not for multiple linear regression, but in simple linear regression, these turn out to be equivalent. If you're interested in it, you can go through the algebra, but that's getting more confusing, the algebra at this point. It's important to note that a high R squared does not mean the model assumptions are satisfied. Um, R squared will always increase the more parameters you add to a model, and so typically we need to adjust it by penalizing it for addition of multiple parameters. So this is something we discuss more when we cover multiple linear regression in lecture 11. This is a lot of code, but it's just plotting all of the different distances from the line in terms of what these different values represent. So I'll skip over the code. Please go through it if you'd like. But this essentially are what each of the components you're predicting in this case. So we have our data points from the start. We have our ordinary least squares regression line that we fitted. We have y bar, which is the mean of the observations in terms of y. We then have the SST, which is the distance from the observations to the to the mean. And then we have the SSR, which is the distance of our estimates to the mean. And then our error component is EJ. Be careful, I did my line underneath the other line. I've just seen the figure. There is so I need to be more careful here, but there is the point is that the SST component goes from this point down to the mean, and then that whole thing can be decomposed into the error component, which is measured from the distance to the best fit line, plus this modeling component, SSR, which goes from the line to the mean. Good figure though. I was impressed with myself on that one. Very helpful. Obviously, very grateful to my AI helpers for the formatting tweaks though, because I could not have coded in all of these arrows working properly on my own, I don't think. Okay, I think I'm officially out of time, so I'll quickly go through. I'm officially 1 minute over normal lecture, so I'll very quickly go through prediction, which is very intuitive. The idea is that once we've fitted our parameters, we can just plug in new observations of X to get out prediction values of what our estimate for Y should be. This is point prediction. So we plug in a value and the model spits out a value for us. This is should have had, I think this should have my noise component involved because this is just the model is fitting the line. And so you don't typically, if you want to have a sample, you need to add some noise. But the idea is we have two different prediction questions. The first one is estimating the average response at X bar. So this is the mean location of if we were to generate them. And then the other one would be a single new observation, which would have this noise component added to it. So the difference is the average response is basically just telling us where the line would be put for that observation. And a single new response would need to take that mean and then distort it by whatever noise we've estimated. All right. So this slide, I very much will skip over for the time being and leave it to be read through in the lecture notes, but you have these two different intervals you can construct for linear regression. One's called confidence intervals, one's called prediction intervals. So the confidence interval is this uncertainty in the mean response. So you're showing the how sure you are that the mean response should lie in this specific interval, whilst the prediction interval is much wider because it's describing the uncertainty of a single future value. Okay, so you can see that it's carrying this extra sigma hat squared. Excuse me, the new irreducible error. So we've got this error term pushing the prediction intervals much wider. And both intervals widen as X star moves away from X bar. And just kind of to visualize both of these two intervals, you can see that the darker blue region is this 95% confidence interval for the mean, which is obviously going to be perfectly centered on the line. And it's quite a narrow band because we're quite sure in this case. And then the prediction interval is this much wider band, which describes where 95% of our values, sorry, it's not that way around. It's the 95% prediction interval is that if we produce this model again and compute the same prediction interval, 95% of the time the true value would lie within it. So skimmed over those last few things a little bit, but we'll be using them quite a lot in the next few weeks. So I'll go through them in more detail then. Just to quickly summarize then, the simple linear regression workflow is always the same. This is essentially automated by functions in Python, but just so that we understand what's happening, we specify the model. So in simple linear regression, it's just a case of defining what our response and what our predictor, and what our response is going to be. We use ordering least squares to compute our values for estimates for beta 1 and beta 0. We can then check the properties. We can perform inference, and we can determine the fit quality before making any predictions. This is essentially the theoretical structure of this type of modeling. And in next lecture, we're going to go over how to practically apply this model. So what are the steps we have to do to first explore data to see whether or not this kind of modeling is suitable? How we fit the model, what kind of code do we use? How do we interpret the summary outputs from those models, and how can we then use the fitted models to make predictions? How can we compute confidence intervals, etc., whilst not having to rely on typing in all of these functions every single time? So yeah, in conclusion, we've covered regression. Hopefully you have a relatively decent, you feel like you've followed along in terms of theoretically defining this type of statistical model. It's very once you're used to the algebra, it's a very simple model and it's very digestible. Make sure you do have a good understanding before we move on to multiple linear regression next week, because the linear algebra can make things much denser and more difficult to intuitively think of as you can move to higher dimensions. We covered what the model looks like mathematically. We covered OLS estimation and even tied it to maximum likelihood estimation. We went over properties of the estimates, as well as covering statistical inference, t-tests, and confidence intervals, etc. And then very quickly at the end, we just kind of mentioned some measures of goodness of fit that we'll get very used to reading from our outputs from Python functions, and talked about prediction and this distinction between confidence intervals and prediction intervals. So next week, we're going on to simple linear regression. Next week, I'm going to record this after this, but on Thursday, we're going to apply simple linear regression end-to-end in Python. We're going to use a stats models package. Some of you may have used it before, but if not, that's okay. We're going to go through all the syntax, and we'll go through a couple of examples and how we structure that analysis in terms of exploration, modeling, residual analysis, conclusions, etc. So yeah, I look forward to going through it then. But thank you very much. Let's figure out how to stop this recording now.